Hello everybody and welcome to the NPTEL online certification course on cryogenic electronics for quantum computing, and this is lecture number 41 where we will be concentrating more on the CV characteristics at high and low frequency. So, just to highlight the outline of the course of this lecture, we will look at the multi-frequency high and low, especially CV characteristics for N and P type at room temperature and down to about 10 Kelvin, and then we will look into the hysteresis which happens at 10 Kelvin versus 300 Kelvin, sort of a comparative analysis of the CV characteristics. Now, just to refresh your memories, if you remember in our previous lectures, we had looked into the fact that if you plot capacitance versus voltage characteristics here, we got something like this, and then this was a low frequency curve, and when we were working with high frequency, this actually came here, and this was the threshold voltage which we are talking about. Somewhere here you had the flat band voltage VFB, this was my accumulation region, this was strong inversion, this was weak inversion, and this was depletion, right. And we saw what is the reason for this, and from here important informations which we were able to extract was primarily the threshold voltage and the flat band voltage. And we also saw that if there is traps available, interface or oxide trap charges, then how does it influence the flat band voltage, that there is a parallel shifting of the CV curve to the left as you make your flat band higher and higher. So, this was what we had learned there. Now, we will be sort of moving ahead and trying to find out the low temperature effects on the CV characteristics, for which this idea is all about. So, let us look at the multi-frequency sort of CV characteristics, and then frequency is changed from or varied from 1 kilohertz to approximately 1 megahertz, and we are plotting capacitance versus voltage right from accumulation. This is my accumulation region, if you see, strong inversion is this one, and so on and so forth. Now, the experimental analysis which has been taken from this paper, this is the source of the paper which I have noted it down. Typically, we use a MOS stack here. This MOS stack is basically an N-type MOS device where the metal is either a gold or a nickel. So, this is my metal plate which is either gold, right, or nickel in nature, and this is followed by either aluminum oxide or hafnium oxide, which is there for this happens to be dielectric, followed by N-type indium gallium arsenide and indium phosphide. So, this is basically MOS stack where the channel is formed with 3,5 heterostructure having either N-type or P-type. N-type it is an indium gallium arsenide, and for P-type it is basically indium phosphide. Below which you have this another conductive glue here, right. Then you have a sapphire substrate, and then there is a chuck on which the whole stack is kept, right. Now, you maintain at 300 Kelvin, we will go down to below your low temperatures, but at 300 Kelvin, as I discussed with you, we are measuring 1 kilohertz to about 1 megahertz the variation. On the y axis, we are measuring the capacitance per unit area of the subject, and on the x axis we are trying to find out the gate voltage, or we are giving the gate voltage, applied gate voltage. So, we have an applied gate voltage on the x axis, and we have capacitance on the y axis per unit area. So, if you look very carefully, this is basically farad per meter square because it is capacitance per unit area. Now, at this stage we will assume that the oxide, which is basically aluminum oxide or even hafnium oxide, at initial stages does not have any interface trap charges or even oxide trap charges, and it is an ideal oxide semiconductor interface, right. The metal which is situated over the oxide and through the semiconductor has got a flat band and a work function difference is already attached to it. With this basic sort of multi-frequency notation here, what we do is that for each gate voltage, so let us say minus 2 volts, it is an accumulation, and we try to find out the capacitance. How do you find the capacitance? Is very simple and straightforward. You apply a DC bias, say minus 2 volts, for example, in this case for an N-type semiconductor, with negative values of gate voltage. Superimpose on that, you give an AC signal because of which a capacitance has been found out. So, basically your capacitance C will be equals to dq dV, right, for a fixed value of Vg. So, you fix the value at -2 volts and then you apply an AC signal over the fixed gate bias, saying that the peak to peak variation may be 1 millivolt or maybe 10 millivolts or 100 millivolts, which is 0.1 volt which you get from peak to peak. So, you have an A sin omega t signal given, and because of which you will see a varying value of charge coming up, measure the value of charge, and from there the incremental charge upon incremental voltage will give you the incremental capacitance. Now, as we can see, as we go to the lower and lower values of gate voltages, we see a much higher capacitance as compared to higher frequency, right. And obviously, if not higher, like if you look at this particular point, then this is with varying frequency. This is low frequency and this is relatively a higher frequency. This is low frequency and this is relatively a higher frequency. If you go to the higher frequency, this is quite interesting, that at accumulation region also you will have almost constant value of capacitance coming into picture, but for low frequency the variation in the capacitance is there with respect to the applied gate voltage. And further, if you go right up to inversion, strong inversion region, which is on the positive gate side here, this is strong inversion, then here obviously the capacitance is a strong function of the gate voltage and it goes on increasing as the gate voltage starts to become higher and higher. Now, now if you look at the characteristics of this curve, then right hand side is basically my inversion region, which is Vg greater than 0. So, this is my weak inversion and followed by somewhere here strong inversion, right, above threshold voltage. Since it is an n-type semiconductor heterostructure or n-type hetero device I have taken, the holes are basically the minority carriers, and you understand this important point, and this is quite interesting issue, that whenever let us suppose you have an indium gallium arsenide or indium gallium arsenide function and you have an n-type material, n-type is the majority current carriers, however holes are basically minority current carriers. Now, when you give relatively a smaller frequency signal, you allow the holes to respond for the AC signal. That is what is written here, if you look very carefully, that you give a time to respond to the AC signal, the minority current carriers, right. So, if you see very carefully at low frequency, I have a variation in the capacitance with respect to applied gate voltage, right. The same thing happens in the inversion layer also, because the number of charged particles are relatively, even electrons are relatively high at the inversion layer, and therefore a small change in the gate voltage actually enhances the number of electrons available for change, and therefore the capacitance changes. So the reason for a substantial large change in the capacitance for the inversion region is primarily because you add more charge carriers, whereas in the accumulation region it is not addition of charge carriers, but primarily the change in the number of charge carriers because of low frequency, and the minority current carriers are able to respond to the change in the frequency, whereas when you go for very high frequency they are not able to respond and the capacitance falls down drastically to a low value of approximately 0.002 femtofarads per meter square. So, when we do a multi-frequency CV characterization at room temperature, two things to be take away from this discussion. Inversion layer is the place where your capacitances are high. However, in the accumulation region, when the frequency is low, the variation is high. When the frequency is high, the variation in the capacitance with respect to gate voltage is relatively low, and that can be explained from first principles of physics. Now, let us look at high frequencies. At high frequencies, obviously the minority current carriers cannot respond quickly, which I discussed with you, and therefore the capacitance is actually dominated by oxide and depletion, which anyway is not varying because in the accumulation region, and therefore it is almost constant independent of the frequency and the gate voltage. So, which part? Which is this part of the curve, accumulation, where the gate voltage is relatively more high negatively and the frequencies are also relatively very high. Now, when you reach to a point where your gate voltage is negatively very high, then at that particular point, since the minority current carriers are not able to respond, they do not come into the picture. So, what are the capacitance which comes into picture? It is primarily the oxide capacitance and the depletion capacitances which contribute, and therefore that lowers the value, right, because they are in series, and in series if you remember 1 by C prime is equals to 1 by C ox plus 1 by C depletion, and it will be, and the overall capacitance will be always less than the least. and that is the reason your capacitance drastically fall down in the accumulation region. Now, if you go on increasing the positive bias, the capacitance starts to increase. So, if you look at the interesting part, if you look at these two curves, the two edges, which means this is basically at 1 kilohertz frequency and this is at 1 megahertz frequency, let us assume, right. Then the megahertz frequency shows a curve which is like this, it goes and then it shoots up and become constants, whereas for low frequency it first shoots down, drops and then it becomes like this, right. So, this is for low and this is for high frequency in terms of overall characteristics. In fact, the high characteristics you will actually see it going down later on. Now, accumulation region, which is left side, which I discussed with you, the electrons basically are the majority carriers in n type and they accumulate at the surface. Capacitances and therefore are almost equals to C oxide, constant value, and there is very low frequency dispersion, which means that with respect to frequency the variation is very small because majority current carriers can respond very easily to rapidly changing frequencies in a sense. Now, please understand, in more cases than other, minority carrier response is highly frequency dependent, right. Minority carrier is most frequency dependent. I will give an example. Why is it? Let us suppose I have an n type semiconductor. So, there are large number of electrons available which are basically the majority current carriers, and I also have holes available here which are basically minority current carriers and electrons are majority current carriers. Now, if you apply AC signal which is of relatively high magnitude in terms of frequency, then what happens is that holes tends to respond much better as compared to electrons for the same amount of charge particle, right. Now, at low frequencies the minority, as I discussed with you, tracks the AC signal and therefore leading to a higher inversion capacitances. Why? Because at low frequency when you track the AC signal, the inversion layer which is basically inverted. So, if it is an n type, we start with become p type, or if we start with p type which is indium phosphide, it becomes inverted with electrons. At low frequencies they track the AC signal. However, at high frequencies when you apply a gate voltage, please understand, when you apply a gate voltage the charge carriers are moving towards the silicon dioxide interface. Now, if you apply a gate voltage AC signal which is very fast varying, right, the inversion cannot be formed at such a fast pace and therefore the capacitance becomes relatively lower in that case. This frequency dispersion or change in the frequency is characteristics of an inversion layer formation delay, right, for an n type MOS capacitor. So, if you start with an n type MOS capacitor, let us take away from the slide, it is all at 300 Kelvin. The takeaway is that when you basically increase the frequency of operation, you do not allow large amount of inversion charges to be there, and therefore, if you see very carefully, if you look at this particular point, there is a bunching of the CV characteristics, whereas here they are all seems to be spread out, right, whereas here they are all bunched together, which means that strong inversion, you have a large amount of majority current carriers at silicon dioxide interface, they do not respond, and therefore the change within the frequency dispersion is very small at room temperature. Now, let us now come down to 10 Kelvin, right, and let us see what happens in the output characteristics. So, this is C versus V, capacitance versus voltage. Capacitance again is in the y axis and we have voltage on the x axis. Now, interestingly, all the CV actually starts to collapse in a single line and it almost behaves like a high frequency CV characteristics, right, and which means that there is no large frequency dispersion happening, right. So, yes, so there is no significant frequency dispersion happening across the full gate voltage range. When there is a big voltage range there, if you see that all the lines have actually merged. So, basically the frequency dependency on the capacitance actually vanishes, right, at very low temperature at 10 Kelvin or so. This is basically a 10 Kelvin experimental graph, and therefore, if you look at this statement, it states that for all CV curve this collapse to a single line, and the single line is regardless of whatever frequency you are applying in this case, right, and therefore all the capacitance versus gate voltage curves are identical to each other. Okay, that is one the observation which we get. It all, and not only that, it also almost looks like a high frequency model of the previous slide. So, if you go back to the previous case, you see this is the high frequency one, right, remember 1 megahertz, and this is how it looks like when you do cryogenic, which is shown here. You see this is it. Interestingly, and this is where I would like to point you out and its implication in circuit analysis, just back of your mind you can keep it. You see, if you look carefully between this region and somewhere this region, right, between the threshold voltages, this is where the threshold voltage of the device will be available. If I try to find out DC dV, which is the rate of change of capacitance with applied DC bias, it is the maximum in this region of operation. So, if you bias your device more than the gate voltage and very near to the threshold voltage, then the rate of change of the capacitance with respect to the input voltage is the maximum for cryogenic independent of the temperature. But interestingly, as you move further and further towards the higher gate voltage, the slopes tends to become more saturated, and therefore the difference in capacitance or DC dV is relatively very small as you go for strong inversion. So, when you go for strong inversion here, your DC dV is very small, right, whereas when you are basically working at weak inversion or near inversion, right, near threshold, your DC dV is relatively quite large. You can ask me what is the implication there. For the implication therefore is that if you DC bias your device in the sub threshold, obviously your current will be small, right, that goes without saying, but the cost you pay for a lower power because of a lower current is typically offset by a larger capacitance variation with small change in the gate voltage. So, even if a small change in gate voltage takes place by even a very small amount, there is relatively a large change in the capacitance. So, if you find out DC dV here, it is maximum somewhere between 0 and Vt, and it is going down as you cross Vt and go to steep saturation, or in deep inversion, in strong inversion but nonetheless one important point from this all discussion is that it is independent of the capacitance, independent of the input frequency at lower temperature. Let us look at the same thing, we will repeat once again here, that the key observations in the inversion region, when the gate voltage, assuming it to be greater than 0, we assume that to be true. Here no capacitance rise is observed at low frequency, right, it is almost the same as here, and therefore it indicates that holes do not respond to AC signals at 10 Kelvin. And so, the behavior at 10 Kelvin for minority current carrier is quite different of the behavior of minority current carriers at 300 Kelvin. There the response was very high, here the response was very low, and that is the reason all the curves have all sort of fused with respect to each other. Second thing is that inversion capacitance is anyway absent because of dopant freeze out as well as non-responsive nature of the inversion layer with respect to frequency. Let us look at the depletion and accumulation region, we have already looked into it. The depletion region is always forming here. So, the depletion region somewhere here will be formed. In the accumulation region, obviously the capacitance will across the oxide capacitance. Why? Because the majority electrons respond instantly even in the cryogenic, and this is quite interesting. At cryogenic temperatures, the majority electrons will respond very fast, the minority does not. At 300 Kelvin just the reverse happens, that the minority responds very fast as compared to the majority one, right, and you need to think why is it so, just think about it and leave as an exercise to you. But 10 Kelvin, whereas one important point to be noted is at 10 Kelvin the majority electrons will respond, majority carriers will respond instantly. Why? I will tell you why. So, when you lower your temperature, your minority carriers are getting freezed out, your majority is freezed out, minorities are getting freezed out. However, the percentage change in the minority freeze out will be much higher as compared to majority freeze out, which means that if they have 100 electrons and 10 holes, once you go to 10 Kelvin, this 100 electrons might go to 90 electrons or maybe even 50 electrons, but the holes will, which were initially 10, that will go to hardly 1 or 2, and that is the reason majority electrons will show a larger sort of respond instantly in case of a 10 Kelvin, in case of 10 Kelvin MOS capacitor. Now, at 10 Kelvin, as I discussed with you, kT by Q, which is the thermal energy, is relatively low. So, I can write down here kT by Q is very small, right, it's about at 10 it will be 30 times smaller as compared to this, so around 1 millivolt right, will be the value of your thermal energy at 10 Kelvin. Now, the minority carrier generation or even electron hole pair generation is severely restricted, right. That is the first point, that the minority carrier generation is severely restricted and it is suppressed, and therefore, there are no extra electron hole pairs being generated. Why? Because at 10 Kelvin your thermal energies are so low that you are not able to promote electrons from the valence band to the conduction band. Then obviously, as I told to you, the diffusions are also smaller because the concentration gradients are not there to a larger extent, right. It would have been there had there been a 300 Kelvin, because at 300 Kelvin are generated and there will be diffusion current available to you because of your gradation in the diffusion constant. But however, when you go to low temperatures, anyway your EHPs are not generated, and therefore claiming that there will be large diffusion current will be a wrong statement. And that is the reason even at low frequency AC signals, minority current do not respond, because they are anyway less in number. When they are less in number and the minority carriers cannot respond, there is what is known as a collapse of the frequency dispersion. Collapse of the frequency dispersion means the phenomena which we are looking at 300 Kelvin at accumulation, all the curves were getting spread out. In cryogenics, it all gets stuck up together, right, and therefore to a larger extent the loss which we have at 300 Kelvin because of frequency dispersion is almost negligible in the case of a MOS capacitor at 10 Kelvin, because they are all fused together and they gives you a single value in that case. Now let us look at the multi-frequency again at room temperature for a p-type semiconductor. As I discussed with you, the reverse will be true here, that 2 volt you will have accumulation because it is a positive side, and of course the reverse principle will be applied in this case as compared to the first case. It point to be noted here is that if you look at this curve and sort of this curve here, these are basically your noise, right, and these happens quite frequently, and we need to find out ways and means of reducing the noise to a low value, right, and this is varying from 100 hertz to 1 megahertz, right. So 100 hertz to 1 megahertz. So the top layer is basically the low frequency layer and the bottom is the high frequency layer which you see, right, and because of which the behavior is exactly the same as the previous case. Now obviously there is a clear frequency dispersion which you see for MOS capacitor in the CV characteristics, and the capacitance decreases with increasing frequency, which has been already explained to you earlier also. Now when you have negative Vg and in the accumulation region, there will be obviously higher capacitance very close to C oxide. Remember, this is almost equals to C oxide, right, and what happens is that so at the accumulation the dispersion of the frequency is very small, relatively small as compared to that in the strong inversion region, and it therefore suggests that the majority carriers can track AC signals at all frequencies, minority cannot at room temperature, right. Okay, let me come to the next one and let us look at the depletion region. As earlier CV characteristics, the depletion region, the capacitance actually drops down, right, and why does it drop down? Because when you are applying a positive bias, your depletion region goes on increasing, right, and when it goes on increasing, the capacitance starts to fall down. That is what happens, and so it is in alignment with our understanding of capacitance. Similarly, frequency dependence increases. Why? Because of reduced conductivity and interface state influence. Let us go to inversion region where we have positive Vg. At low frequency the capacitance increases, and at high frequency the inversion at all is not formed, exactly the same reason as we discussed earlier, and therefore there is a lower capacitance available with you. Now let us do the same thing at 10 Kelvin, and we do the same structure of indium gallium arsenide or indium phosphide, which is a p-type, and we are fixing the temperature at 10 Kelvin. So this is basically for a cryogenic temperature, and we vary the frequency range from 100 hertz to 1 megahertz. And as you can see, let me observe, let's look at the detailed observation here. There is a significant dispersion which is clearly observed in the accumulation and the depletion region. You see, in the accumulation and the depletion region you have still substantial dispersion with respect to frequency is observed. However, when you go to strong inversion, that dispersion vanishes and you have single value of capacitance which you get in this case. This is a p-type semiconductor, please understand. So, interestingly, one observation is that, which is point number 2, that unlike in n-type devices, the dispersion persists even in the accumulation region, which was not there if you remember in the previous case. Let us look at the inversion region, and it goes down to approximately 0.002 femtofarad per meter square, and therefore this indicates the absence of minority carrier response even at low temperature. So, what has happened in low temperature can be explained in a very easy manner is that two things is happening. Inversion layer formation is getting difficult. Not only that, you do not allow minority current carriers to get generated in a sense and give you a change in the capacitance value. Now, what we will do is that we will vary the gate voltage from a negative value to 0 to a positive value, and we will plot capacitance versus voltage, and then we will start bringing the gate voltage right from say 2 or 3 volts down to minus 2 or 3 volts. And interestingly, what we see is that there is a hysteresis. Hysteresis means as we move our gate voltage from low to high, the path of capacitance is not the same as the path of the capacitance when you come high to low. So, low to high transition capacitance and high to low capacitances are different, and that can be seen here. Look at 0 curve here, right. Then this point and this point is different. Similarly, if you plot a graph here, then this point and this point are different. Typically, when you reverse from higher positive value to negative value, the effective capacitance is higher. This is known as hysteresis. And why this happens? See, it will follow exactly the same curve provided the change in the charge with respect to voltage is same as we move from low voltage to high voltage. However, the difference is coming out because of the fact that when you have a larger voltage, the electric fields are larger, it becomes more difficult to trap or detrap a charge carriers, right, and therefore they are separated for a longer period of time, and that is the reason there is a dispersion available to you. Even at 10 Kelvin, this problem is there. There is a problem of trapping and detrapping. Now, we do a hysteresis over a period of large sweeps, and we see that the charge trapping is reversible even at cryogenic temperature, right. So, when you go from lower voltage to higher voltage gate voltage, you charge it, and let us suppose from higher to smaller when you are coming, you are discharging it, but the paths are not same, and therefore there is a sort of a hysteresis window available at 10 K and 300 Kelvin. Now, at 10 Kelvin, as I discussed with you, though in accumulation the frequency dispersion is gone, it is not there, you still have hysteresis available to you. See, just look at this T equals to 300 Kelvin, this is T equals to 300 Kelvin, and this is T equals to 10 Kelvin, and that is the challenge which you will face, that the area under the hysteresis curve is much larger in case of 10 Kelvin which you see. So, around 10 Kelvin you will see a substantial amount of change here, and the physical reason can be found out analytically as well as numerically. Now, so let's finish off our understanding of CV characteristics at 10 Kelvin and 300 Kelvin. Where are you giving the gate bias? Giving it on the gate side, right. When you apply the gate bias, right, electric field is generated in the oxide layer, and this actually helps you to either capture or emit charge particle depending on the direction of the electric field. Now, at cryogenic temperature, the field, so your thermal energies have almost gone, right, it has become almost 1 millivolt, which is not even enough to promote electrons for a silicon. So, who is responsible rather than the thermal energies is the field, electric field, which is responsible, and they actually dominate the trap dynamics. So, let us suppose you did not have applied any field, you are varying the temperature. At 300 Kelvin, you will be actually helping the charge particle to get detrapped from its trapping position and appear as a single element. However, if your temperature is being switched down to 10 Kelvin and your electric fields or biases are also 0, nothing will happen, you will be able to enter into a full state of equilibrium. However, if you start doing the hysteresis window and try to find out that if you lower the temperature at 10 Kelvin and then do the same process, there will be detrapping taking place, right, and this detrapping will help you to understand the dynamics of the device, right. So, with this, let me recapitulate what we did in the last around half an hour for this lecture. What we did was we tried to find out initially the CV at low and at high frequency. We took indium phosphide and indium gallium arsenide and we tried to see the trapping phenomena and its CV with respect to frequency dispersion, right. And the reason we are doing it is that we want to study that if you are working in cryogenics, then at which bias point your capacitance will be maximum. Then let us not operate there, because if you do that, then you end up having a larger time constants and therefore larger delay in your output signal. So, the reason we discuss this topic is to see which bias condition at cryo gives you the best value. Then we saw a 10 Kelvin and 300 Kelvin sort of CV hysteresis and try to enumerate on why the CV hysteresis is happening. Primarily happens because the majority and minority current carriers do not respond to the reduced temperature in the same manner, and therefore the change happens when we discuss about this. The last point which we did was that we see a wider hysteresis window at 10 Kelvin, right. So, you see, if you look at the area under the curve, which is basically this one, you will see that the red one has got a more area as compared to the black one, right, and therefore the hysteresis is maximum at 10 Kelvin as compared to 300 Kelvin. So, with this, let me stop here today, and while we meet next time, goodbye.